as he said, today is Friday, so we're going to relax with MATLAB on Friday. How about that? Is this on? Yeah. So, since the last week of January, kind of the last week, I won't be here. I'm really sticking to last year's lectures, almost word by word, and even with problems and examples. Well, first of all, because they make sense. But I want to transition to the videos that I will give you in an easy way. But also, I will start today showing you some MATLAB code, and I've changed a few lines of code with respect to what I had last year. So as I said a couple times already, stick to this material that I give you this year, because I may change a couple lines of code to do something completely different. So it's already posted. What we'll see today, it's already posted. And what we're going to do is partially solve the problem and then do something more exciting than just that. But the bottom line is that we left off by saying, OK, before I write the equation, actually, if I have an inertial observer somewhere, but I really want to sit on my planet M1 and look at what the satellite M2 is doing, I can, as long as I choose a reference frame that doesn't change orientation with respect to the reference frame of the inertial, the coordinate system that doesn't change orientation with respect to the coordinate system of the inertial observer. So what we call ECI, Earth Center Inertial Reference Frame. So if we pick that, this vector here, R double dot, that this observer sees changing according to this gravitational law, well, I basically measure the same kind of behavior from this perspective. So I can almost forget about that and work in that basis, which is what I want because I am sitting on the planet. And we said, OK, if little r is expressed in some basis there as xi plus yj plus zk, where, of course, I, j, and k are the unit vectors defining your coordinate system. Obviously, this is a vector expression, so it's 3 components. I have a second time derivative. I'm looking at 6 scalar differential equations. Well, yes, eventually I will look at 6 of them. But we said we need 6 constants of integration to actually have what you want when you're integrating that. Basically, you want a r of t, some kind of function or points in time that tell you how the position is changing if you integrate numerically. And of course, you want a velocity in time, r dot. So that's what you are looking for if you're saying that you're integrating those equations. And we also said, well, these, once I switch to these coordinates, corresponds to the following equations. X double dot equals minus mu over, let's just leave it at what it is here, x y double dot equals minus mu over, this is the square root of x squared plus y squared plus z squared all cubed. And finally, z double dot is minus mu over this expression z. And we said we're going to change variables and call x1 x, x2 y, x3 z, x4 is x dot, x5 is y dot, x6 is z dot, so that substituting in these equations those quantities, I actually get 6 differential equations, but all time derivatives are no more than first order. It's just a change of variable. And let's rewrite how that system will look like here. If I do that, let's see. Well, what I'm going to do is I'm going to take the time derivatives of each one of these. So if I write x1 dot, that is equal to x dot, but that is also x4. So that's my first equation. Then if I take the time derivative of 2, x2 dot is y dot, which is x5. x3 dot is x6. And now I have those equations popping up, because x4 dot is x double dot, which is this part here. So x4 dot is minus mu, whatever it's down here, then I'm not going to rewrite. X is x1. x5 dot is equals to minus mu, whatever is down here, x2. And x6 dot is equal to minus mu this times x3. And so here are my 6 differential equations, first order now, that I've obtained by the changing of variable. So again, this is what people do for dynamics and controls, and this is what MATLAB takes to integrate numerically a differential equation. So you have to bring it into this form. And what happens is, I'm sure that all of you are familiar with the E45, right? You've used it multiple times. So am I wasting your time here? No? Okay. But what MATLAB will take as an input in the function that you will integrate with ODE45 is this right-hand side, which is the time derivative of your state vector, and it will integrate these at each time step to give you what? When you integrate these 6 variables at each time step, you get x1, x2, x3, x4, x5, and 6, which is position, these 3, and the velocity. Make sense? So that's what you generate when you integrate that system. And so this problem is exactly asking you to do that. It's 2.3 in your book. Let's see if I can make it bigger. Big enough? Better? Yeah. Okay, so relative to a non-rotating frame of reference with origin at the center of the Earth, which is what we want to use, a ton satellite, 1,000 kilogram satellite's initial position vector is 8,000 I plus 6,000 K. So if you want, it's a good idea, at least for simple problems, to draw a little sketch to see what it is that you have. Okay, so if now this is ECI, my planet is at the center here. They're telling me that I have 8,000 on X and 6,000 on K on Z, right? So this is I, J, K. I don't know what 8,000 here is. Let's say that it's here. 6,000 is a little less. So your satellite is somewhere on this XZ plane, okay, at initial time. I'll tell you right away this problem has an error. In fact, you know this here, that they tell you that's the initial velocity, then they go here and they just change it. I have no idea why, but so if we go with that velocity, 7j kilometers per second, that means the initial velocity is only projected on the y-axis. So this object, your spacecraft, is initially moving parallel to the y-axis with the initial velocity. So in other words, this would be your r0 vector, and this is your r dot 0 vector. Again, r0 is in the plane of I and j, while r0 dot is exactly orthogonal to that. So it's moving this way, parallel to j. At least with that value, then they change it. They ask you to use a algorithm at the end of the book. I'm not going to do that. I have my own code, but it's doing the same thing. To solve for the path of the spacecraft over the next 4 hours. So that's time 0. You want to integrate that equation that I have erased for 4 hours. And then you want to also determine what is the minimum and maximum distance from the Earth's surface during that time. Over the 4 hours. And so they start saying, okay, use the MATLAB function, whatever they give you, and the initial value is that, which doesn't match what they just gave you, but they're changing it. So with that, you will basically have, let's see, 0 on the x, no component on the x. They give you a velocity that has a component on the z and on the, I'm sorry, no, on the x and on the y, no component on the z. And I do have the values, I don't remember which one of the two, we'll play with them. One of those two combinations actually matches the solution. But what we care about is how you do this. Okay, so this is all posted on your on my website, on Canvas at this point. The first thing when you have to integrate a differential equation is you have to find a way to write that differential equation. You write it as a function, and then outside ODE45, we'll call that function multiple times and integrate it at each time step. So the x1 dot, x2 dot, x3 dot, etc. This is assembled into a function, and it will be taken by the numerical integrators of MATLAB. There are several, not only ODE45, to give you this at each time step. I go. So this is what I gave you. It's a function. It takes, I call it relative acceleration. You have to make it a function of time and u. U is basically this. It's the vector of 6 components, x1 through 6. Just called it u. I could have called it x. A few constants. G, the one we introduced last time, that's the mass of the Earth, m1. Can you all see the numbers, more or less? As you see, it's 10 to the 24th kilograms. A ton is 10 to the 3rd. As I said last time, you really need a pretty big spacecraft to be comparable to the Earth. It's really not possible. At least so far, we haven't been able to build anything like that. The moon is probably close, comparable, but not what we can build. So I still have the mass of the satellite there, but it's really just for fun. Because if I run this, I don't know if I can do it here because this is a function, but if I just copy all this stuff and run it here in MATLAB, mu is this value, okay? Now I'm going to redo it by saying that the satellite has no mass, and mu is exactly the same. I mean, you can go with format long and try to appreciate if there are any differences, but I really doubt it. So M2 is really irrelevant. You can remove it, but it's there. And now, what am I doing here? I'm doing exactly what I wrote before. I am assembling the input, which is x1, x2, x3, x4, x5, and x6, so that I can generate as output what is called the dy, the time derivative of this vector. And remember, should probably rewrite it entirely here. That was x1 dot, so that would be the first component of dy. It's x4, so u4 in this case. x2 dot, second component, is x5. x3 dot is x6. And then remember, x4 dot is the actual equation. Minus mu over all this quantity here, square root of x squared plus y squared plus z squared, cubed times x1, etc., etc. I just have a change of variable here. X, y, and z will be u1, 2, and 3, but you don't have to do that. So, but that function is only taking, at each time step, the state vector, position, and velocity, and is generating its rate of change, its time derivative. Make sense? No? Yes? You probably have seen this stuff before. And so now these will have to be called by a numerical integrator over time. So at each time step, you integrate, then you go to the next time step. So you're creating points in time of positions and velocities, and then you can plot those points. So this is my main file. A few instructions at the beginning that are always useful. Clear the screen, clear all the variables, close all the figures that you may have open. That's the radius of the Earth, 6,378 kilometers. And that is the position I have, which is the one at the beginning of the problem, not the second one they give you, because I think that's the right one to get at least the answers they have. And now, I'm using ODE45, so I'm going to jump to this line for a second. This is syntax that you can just find out by typing help ODE45. But what you do is you're calling a numerical integrator over this function that I've just discussed. So that's my differential equation / equations that I want to integrate. I want to integrate them over a certain time span, which is defined here as from 0 to final time. And as you can see, this is 4 hours, 3,600 seconds times 4. I have a 1 here in case you want to put days, which we will do probably as an exercise. And then this is your initial condition, which is assembled as a vector. Remember, the relative acceleration function here is spitting out a 6-component vector. See? This output here is a column vector in MATLAB with x1 dot, x2 dot, x3 dot, etc. So it's 6 of them. So you need 6 initial conditions. And so it is assembled by the numbers that they gave you. initial position, initial velocity, you just put them together, and this is final time, 4 hours. And then I plot in 3D what ODE45 will give me. You can output more things, but this is the default minimum output that you want from a numerical integration, which is the time steps and the corresponding solution. So T out will be a vector of times, and Y out will be a matrix where at each time you have 6 values, x, y, z, x dot, y dot, z dot, position and velocity. Do you have any questions? Is this all clear? It's almost boring. Okay. All right, so if I run this up to this point, it should not crash, first of all. Yeah, it didn't. And I have a simple sphere instruction. At some point, I'll probably give you some code, or some of you will figure it out, where you can actually have texture of the planet there. Last year, one student gave us the code. He found a way to make that look like the planet, which is really nice. So as you see, this is an orbit, not even an entire orbit. I think the star there, it's the initial point, if I'm not mistaken. Did I put it at the initial point? Yeah. So that's where you start. I didn't draw the axis. You can draw the x, y, z axis. I mean, they are here, but not coming out of the planet, which will be easier to visualize. So this is your trajectory. Almost an entire orbit. It is definitely not a circle. It's a little eccentric. No surprises. And so the questions they're asking you is, what is the minimum and maximum altitude, and what are the velocities at those locations? And for those of you who have used the min and max commands, they're pretty simple. You look through a vector, it will return, in this case, the minimum altitude. So y out is a vector of positions and velocities. The first 3 components are positions. And you can also return the index in that vector, at which location you have the minimum or the maximum. So that's what I'm doing. Are you familiar with the debugging in MATLAB, what I'm doing here, going step by step? Done it before? Some of you may have, some of you not. It's extremely useful, and the only way to fix your code, because I don't know about you, but the first time I code something, it usually doesn't work. Okay, so this is telling me that this is the minimum altitude. Well, I have to subtract the radius of the planet, because they actually talk about altitude over the surface. So it's 3622, which is this value here, so that works. And also, I know that it's actually happening at the first time step, because the index is 1. So I take that index and input it into the other 3 components, the last 3 components of the y out vector, which contains velocities, and compute the velocity at that particular location. And the speed is 7 kilometers per second, which is what they're telling me here, right here. And then I go with the same max altitude, max speed, 9574. It's more or less the same. This is not exactly the same. I don't know why. This book has some errors here and there. Speed, I cannot see it. Speed at max should match what I have on the book for you. 438, yeah, 439. All right, now this is the not that fun part. I added some stuff. So if you uncomment these last 3 lines of code, this is now repeating another, it's just doing another numerical integration, the same time span, the same initial conditions, everything is the same. I am using a different function that I gave you that I cannot explain at this point, but I will at some point in the semester. This is a more elaborate model for the gravitational attraction between the satellite and the planet. It's more than the simple Keplerian dynamics. So this is what we had before. This additional pretty long expression, it's a way to model an oblate planet, which is also called J2. We'll explain why it's called that way, but you just believe that that's a more elaborate model for the attraction. So this is just to justify why we really want to do perturbations and talk about them in the future. So if I now run this code, this will plot the trajectory with a simple first model, the one we just did, and the trajectory when I have a more elaborate model of gravity, which is the second function. And I don't see any difference, right? I mean, you can probably move around and see the blue and the red barely on top of each other. I mean, really on top of each other, so you can barely see the difference. That's 4 hours. Let's say that I just go around, I don't know, 4 days. See the difference already? They are not on top of each other anymore. If I remove the blue trajectory that hopefully I'll be able to select, the red one remains really on top of each other, of itself. It doesn't change with time, despite of the numerical errors you may have. And I don't think I've discussed the time step that I have here. What do I have? Yeah, maximum time step. It's. I'm sorry.
The blue one, the previous one.
The blue one is the new one, the one with J2, is the more realistic trajectory. Okay. So here time step is 10 seconds. So it's a pretty good numerical iteration in terms of approximation. So if I keep going, you want to do 10 days, 15 days, do a couple of weeks. So this is a satellite, which, by the way, has initial conditions that are in low Earth orbit. It's not a very high satellite. So it's very relevant for most of the spacecraft we launch. It's still running, of course, because this is now 2 weeks. See, they really are starting to diverge. And here you're talking, we cannot really appreciate it from the plot, but you can imagine how many, kilometers you're talking about. The blue trajectory is really not staying on top of itself over just 2 weeks. So this is just my way to justify to you all the painful math that we'll at some point discuss to model a better gravitational field for the Earth, because that's just a little more realistic than the red line. There's also other things that happen, but stopping at the red trajectory, Keplerian dynamics would be really a bad approximation, because this happens only in 2 weeks. If you keep going, you can run this code for longer. You will see how the two diverge over time. So if this was a satellite needing to stay on top of its trajectory, initial trajectory at all times, you will have to do something to correct all these issues. One, I'm just going ahead of myself, but this reality that we have to live with, the J2 for now. Now, you may say this is bad. Yeah, it is bad. It is a perturbation that is going to change my trajectory, but there's some benefits that we can get out of that effect. There are some special inclinations where, for example, you see the trajectory is here, it's kind of rotating in space. Do you see that? The red one is just staying there, but the other one is changing over time. I can run it for longer, you will see it even more. But the plane of the trajectory is definitely changing. Let's just do an entire month if this doesn't crash. Well, one pretty useful application of this effect is that you may be able to actually have your trajectory always pointing at the sun, because it's rotating naturally because of the shape of the planet. And so if you insert your satellite at the right angle, the initial plane, and you construct your initial trajectory in the right way, you can actually just have for free a continuous rotation of the orbital plane at the same rate as the planet goes around the sun, and you see light continuously. And there is a pretty bad bug flying there. That's kind of scary. Go away. That way. Hey. Yeah. This is astrodynamics. It's not flight dynamics. Go. I don't like those things. I'm sorry. Just let me know if it gets close. Okay, so say that. No, this is not the Earth. This is the sun. Where is it? Sun. The Earth is going around the sun. I'm a little nervous. The Earth is going around the sun, right? So over an entire year, it will be at different locations. And what we are plotting there is whatever we see from these bases that doesn't change orientation over time, right? So we said I decided to keep it fixed in space no matter what happens. And what I am observing there is that that effect, what the blue trajectory is doing is changing. So I may be able to exploit that. Again, don't take notes. This is just, again, just explaining that perturbations may be bad, but they also be useful. You may be able to, at initial time, say this is your initial orbit insertion. You put your satellite in such a way that the orbit is always illuminated, right? So in this particular initial orbit, you always see the sun. You're never behind the planet. You don't get any shadow. But if nothing would happen, then here you may actually see some shadow, for example. It could be the case. But if the orbit itself is rotating with the planet, rotating, at the same rate as the planet is going around the sun, you may remain with this face, that is your orbital plane, looking at the sun all the time. I know my 3D sketch is probably not that great. This is probably better. This is the orbital plane, and this is the sun. You may obtain something like this, where your satellite is never behind the Earth with respect to the sun. Those are Sun-synchronous orbits. They are used and abused because they are just free of maneuvering. You don't need to maneuver. Another simpler way to sketch this would be, if you allow me to do it here, if we just stop at 2D, is basically that this is your orbital plane now, this is your orbital plane now, this is your orbital plane now. If we just look at the problem from a two-dimensional point of view, you can remain, for example, always at 90 degrees with the sun, so that the satellite is moving in this plane, but is never behind the planet. Make sense? So these are orbits we can obtain at different altitudes and different inclinations. There is a relationship between altitude and inclination, so that that effect, which is completely free, you don't have to use any thrusters to have this rotation of the orbital plane, matches the angular rate of the Earth around the sun. So
Alright guys, so unfortunately there's been a problem with the microphone. I realized that the last 10 minutes of the lecture are have the audio corrupted, so I'll try to cover that with this additional sound. So at this point, I believe we had discussed already what happens with the effect of the oblateness, and I was going to add possibly, thrust as an additional acceleration just to the Keplerian function, the rel acceleration function, not the one with J2. So, for example, when we will see maneuvers, we at some point will see continuous thrusters used. We may have the ability to fire an engine that increases the velocity and fire it in the direction of the velocity vector itself. So right now I'm describing in MATLAB an additional three quantities that are basically, when you put them together, the velocity vector. So u4, 5, and 6 are vx, vy, vz, so that I'm going to be able to define a constant thrust, either positive in the direction of the velocity or opposed constantly to the velocity, which is a very poor and high-level representation of what you would see with the drag force, for example. You would see something that is constantly opposing your motion, and that's what happens, for example, in low Earth orbits. Below 700 kilometers, there is some atmospheric resistance, which may be not negligible at all when you have a big surface and heavy spacecraft. In fact, the International Space Station does thrust. Okay, so what I'm discussing here, hold on a second, about the ISS, is that the last three components of this dy is what you need for is your dynamics. So if I add a thruster, an acceleration due to a thruster, it will go it will have to be added to that term. So as I was saying before, the ISS, for example, has to reboost every so many days, I believe a couple of weeks, to keep the altitude due to the fact that it's decaying because there is a little bit of atmosphere. So here I'm going to sketch a generic time where you have a satellite at a given position r and possess it as a given velocity that I'm just gonna call v, that will be your r dot, and assume that there is a thruster that I can fire, for example, constantly in the direction of the velocity, pushing with the velocity. And again, it could be the other way if there was a resistance or a maneuver where you are required to push down. And so in terms of expressing that thrust as a vector, say that it's a constant t times, if it's with the velocity, it will be v normalized. It's the unit vector of velocity, so it's v over its norm, and that could be a constant thrust. And I'm going to code it in MATLAB by using the vx, vy, vz expression that we have defined. So t will be equal to sine t0, that I'm going to define in a second as a constant 10 to the minus 6, I believe I started from on top, times the unit vector of v, which is, of course, it will be the vector vx, vy, vz over its norm. So that will happen in a second. 0 times the entire vector over its norm. Okay. X, vy, vz. Just copying it into the norm function so that whatever is multiplying t0 is a vector in ECI pointing constantly along the velocity of the spacecraft. And so since my dy is what it's outputting here is velocity and acceleration, this will be an acceleration generated by a thruster. So I will add it to the last three components of the output. And keep in mind this is per unit mass, so it's kilometers over second squared. These are all accelerations. So removing the J2 part and integrating for a little less time, I think I was doing a day, and you start appreciating that the trajectory is not, this is pushing with the velocity, it's not always on top of itself. It starts to change over time. And I think the next thing we did is increasing one order of magnitude the acceleration, 10 to the minus 5. That will give you a spiraling out acceleration, which is what you get with a continuous thruster that it's able to push with the velocity, maybe very tiny force, but constantly there. This is what you get with electric thrusters, for example. Constantly there, increasing the size of your orbit until you spiral out and maybe leave the attraction of the planet. That's trajectory transfer maneuvers done with continuous thrusters, for example. So let me pause right here. So change that. Yes, higher thrust gives you this spiraling out type of shape. And this is now changing the sign. What I've just done is changing the sign to that acceleration, putting a minus in front where you're spiraling down, you're going in to the planet. As you would experience with the drag force, you're losing altitude up to the point of basically re-enter the atmosphere, and the drag force becomes more important than gravitational attraction, almost, or comparable, so that at that point you really have to talk about flight mechanics and not just astrodynamics. The drag force is not a perturbance anymore. It becomes same order of magnitude. You're not in orbit anymore at a certain point. And I think that is one question that came up right there. In a second, I'm going to actually write that the acceleration due to gravity plus the acceleration of drag or whatever is pushing against the velocity, you can say that it's that it's still representing an orbit until the point where it doesn't anymore, because the acceleration of drag is taking over. It's comparable. So here we're discussing ISS maneuvers, how you have to every once in a while regain altitude through thrusting, and I think really this concludes my audio recording to make up for corrupted audio, and I apologize. Should have recharged the batteries more often, apparently. So yeah, exactly, that's what I'm saying, is if the drag force becomes strong, then you're not talking about an orbit anymore, you're probably talking about orbital mechanics, spaceflight mechanics as an aircraft. And I believe that the rest of this video will be silent. Sorry about the little accident.